Hi, this is Preston Culbertson. I'm in Physics Lab M06, and this week I'm going to be going through Lab 1, which is motion with constant velocity. So my main results of this lab is that when F net, or the net force of a system, is equal to 0, it will be undergoing constant velocity. And so my system this week was an air hockey puck, which I took video of on my iPhone, and I put the video into a program called Tracker, which allows us to model the movement of something in a video. And I set up, in this video, the puck will be moving with a constant velocity in this direction. So I set up the axis where the puck will be moving along the x-axis in the positive x direction. And as we can see, this is a calibration tape, which allows us to put the size of the puck in the video so that we can get proper scaling. And these red dots that appear behind the puck as it moves are point masses, which allows us to track the movement of the center of mass of the puck as the video goes forward. So to make a computational model of this, I plugged in a few initial conditions into a program called VPython. I plugged in the mass of the object, which is 0.042 kilograms, or 42 grams. I also plugged in the initial position from the tracker data, as well as the initial velocity, which I calculated using the average velocity equation. That's the initial, or the final position minus the initial position, which both come from the tracker data, over the delta time, which is the elapsed time in the video, which is about 0.8340 seconds. And so that gives us a velocity during the video of 0.880 meters per second. And so to calculate this, I ran a while loop that steps the time forward by this 0.0333, which is about, it's 1/30th of a second, which is the time elapsed between point mass measurements in Tracker. And so in this system, there's no net force because all forces cancel out. And I used Newton's second law to calculate the new velocity of the ball each time. So that's the final velocity here minus the initial velocity here is equal to, the final velocity is equal to the initial velocity plus the net force over the mass times the delta time. But since F net right here is equal to 0, that means that the final velocity is equal to the initial velocity, which gives us our constant velocity that we're looking for. So this is my Python code that I'm running in VPython. I'm just going to run the simulation for you guys. You can see it plots a ball, which simulates the puck. And so over this 0.83 seconds, you can see it moves to the right with a constant velocity. And this is our graph of velocity over time. And so we can see that it has a constant velocity as time goes forward. So I'm going to pull up the data from my simulation. I took the data from Tracker and the data from my simulation and plotted it on the same line graph. What we see is that the trend actually follows really well. It maps the data from Tracker pretty well. As you can see, the line's a little shaky from Tracker, but that's usually because of human error. The pointer is not too precise as we go along, but we can see it's a pretty good trend, and so the model works pretty well. I'm going to go to the what if question, which is what if the axis is at a different location? And so what I thought is, what would happen if we moved the axis down by 1 in the y direction? And so another way of saying moving the axis down by 1 is by moving the initial position up by 1. So I'm going to run the Python simulation. As you can see, instead of starting at the origin here, it starts just 1 up. But we're still going to get a constant velocity in the positive x direction. So moving the origin in the y direction has no effect on the direction or force on the velocity of the puck as it moves. Now I'm going to go to the what does it mean question. And the what does it mean question is it possible to add up all forces for F net equal to 0? And my answer to that is yes. In this system, there's only 2 main forces acting on the puck, which is the force of the air from the table and the force of gravity moving down. And those forces are equal and opposite. And so that keeps the velocity constant as it moves across the table. There are a few forces of air resistance and friction on this puck, but since it's so small, and also since it's moving across a bed of air, I would say that those forces are negligible and they don't really factor in. Now I'd like to show what happens if the net force is not equal to 0. And so what I'm going to do is I'm going to add a force in the y direction, which to give a physical picture of what's going on, that means if I turn the air on the air hockey table way up so that the puck just started to fly off the table. And so what that does, when we run the simulation, as you can see, the puck like flies off the table in the y direction. And so, as you can see, the force in the y direction actually gets the ball to change direction. And so there's no constant velocity. It's actually accelerating upward in this y direction. And so that means the velocity is not constant whenever the force is not equal to 0. So those are that's the main results for our lab. Fnet, when Fnet is equal to 0, we have that constant velocity we're looking for. And when it's not, we get acceleration or change of direction. And that's something that will be covered in later labs. So thanks for watching.